It seems we cannot hear you. There seems to be some technical issue as I see Razvan, but I don't hear anything from your side, although I see your slides.
Okay, can you hear me now?
Okay, now, perfect, good.
Okay. Let me try to share the screen as well.
Okay.
Okay, thank you. Thank you.
Now the sound, you're mute. Now, no.
So, okay, so it seems that whenever I share my slides, my mic turns off, and I don't know why.
Yes, it's very strange.
I can do, yeah. What I can do is I'll quickly convert them into a PDF and present them that way. Maybe that will, because I'm worried that it's. Sorry for the sorry for all of this.
No problem.
Okay, and now trying to share screen. Okay, now you should be able to hear me, right?
Yes.
But okay, sorry.
Yes, perfect. This should work.
Okay, yeah, sorry. My slides are a bit of a mess, but because of this, let me. Okay. Thank you so much for having me. So I guess I wanted to have a short talk that's a little bit more high level, and I wanted to focus on. Yeah, the question of like how should we think about continual learning, and you know, I will start basically very similar to I guess Hava's talk, discussing what continual learning, lifelong learning is supposed to actually be, and the next like 3-4 slides are slides that I always have in my talks, so maybe some of you have already seen them. But usually, I think as a community, we haven't yet agreed what is the difference between continual learning and lifelong learning. And I would venture to say that there are actually additional terms that people use now that I still don't know what the difference between them are, like never-ending learning and so forth. And somehow all of these things relate to having a system that's able to learn in a non-stationary setting, you know, able to continuously learn as things change in the environment. And I think the most pragmatic or the most descriptive definitions of these terms usually end up by describing the setup that you're supposed to use when you're trying to do research in this space. And for continual learning specifically, but I think for lifelong learning is the same, you usually start by saying, well, you have a series of tasks that you have to go through and you have to learn them sequentially, and somehow at the end of the day be able to perform well on all of them. And this setup tends to have a lot of variations. So you tend to have, smooth task transitions, discrete task transitions, and we just had a question about that before. The task length and repetition might be different. You could receive task, or each task you see is unique. The task types can be different. So you could have unsupervised task, supervised task, or reinforcement learning, or other things. And you might even have situations where there are really no tasks. There's just a drift in the distribution and so forth. Okay. Besides the protocol that you'd have to follow to train a system, another thing that usually is described in this kind of definitions is what you'd expect your solutions to do. And this usually, or I've seen many times, this comes as a long, like laundry list of wants, right? And you would like to have minimal access to the previous task. That's one thing that's, I think, quite popular. And usually, because of that, you have to deal with things like catastrophic forgetting. You might want to have like minimal increase in model capacity or computation. So you want things to stay scalable as you go from task to task. You want to minimize catastrophic forgetting or interference. You might want to maintain plasticity. So I think this is not something that's discussed a lot in the literature, but there are papers that have noticed that as you keep learning, you either make learning really hard on the new task, so it can be seen as an optimization problem, or what can happen is you can easily learn the new task, but you will not generalize in the same way as if you'd learned this task from scratch. So this kind of loss in plasticity can happen, particularly for in supervised learning, where it's kind of easier to measure, and it's something you'd really do not want to happen, right? You'd want your system to be able to learn as efficiently as you go through. And you might want to maximize forward transfer. So like a big theme in continual learning was always that you would learn all of these things and you would remember them such that you can utilize them to learn faster as you move forward. However, when you put all of these things together, you get a lot of contradictions and dilemmas, right? So some of these things are opposing each other. That we have more and more evidence that as you're trying to solve catastrophic forgetting, you're doing that at the expense of forward transfer. That might be just because of how the tools we use and how we do it, but it's still sort of something quite problematic. Obviously, some of the ones, if you take them ad literam, are also don't really fit together. So for example, a fixed capacity model, which is something sometimes people require from a continual learning system, is impossible to do at the same time with dealing with catastrophic forgetting, right? The finite system cannot remember an infinite number of things. So at some point you need to give something, right, to get these things to work. And the biggest issue is, so there's a few issues. There are different protocols, and different protocols highlight different aspects of this desiderata. So then one question is, sorry, I'm pretty sure this would be on the next slide as well. Yes. So one question would be, what is a full taxonomy of all these different protocols that we might care about, and why would we care about all of that? Like, which of them we care, and why do we care about that particular protocol? And the other important bit is many of these trade-offs are really like hidden in the data. So if we're taking, say we're interested in forward transfer, right? We care about the system to be able to learn more efficiently on a new task utilizing information from the previous one. It's a bit unclear why that should even happen in a scenario like permuted MNIST, where we explicitly destroy any structure in the data. So it's unclear what exactly you'd expect to reuse from the previous permutation of your data as you move forward. Or if we're looking at Atari, sometimes this is very unclear either. And we've played with Atari in the past, for example, in progressive nets, and it's very unclear when and why you should even expect to have any form of transfer between one game or another. The same time with catastrophic forgetting, right? In some of these scenarios where you have like a smooth transition or like a continuous drift, forgetting might not be as problematic as we think, and certain solution for forgetting would work while others would not. So I think this kind of leaves the community in a little bit of dilemma, so to say, or leaves it in a bit of an unsure territory where we're building methods, but we're not exactly, it's really hard for us to specifically say what these methods are, you know, what are they good for, where do they break, because they might outperform a different method on a particular benchmark, but they might not on a different benchmark. And these benchmarks, to a big extent, are all artificially made by us. And also, it leaves us in a state where we start building new and new protocols for continual learning, new variants for continual learning, which kind of makes the whole field a little bit too open-ended and not constrained enough. And I wanted to, like, the way I've been thinking about continual learning lately, and I'm sort of wondering if others will find this useful or not, is to try to think what exactly we're trying to solve. So if I have the solution for a continual learning problem that I'm really looking for, well, what exactly am I supposed to use it for? What is it going to do? right? And I wanted in the next few slides to give a few scenarios that I thought of like how you can think of continual learning and what it can be helpful for, and then from that try to draw some conclusions, and yeah, maybe leave the stage open for questions and just sort of discussion on this topic. So one particular scenario that actually I found out by just being invited to a workshop where this scenario was discussed, but I find it quite interesting, is this idea of continual semi-supervised learning. So the idea here is what you'd expect the continual learning system to do at the end of the day is to maintain a large scale system up to date as you know things change in the outside world. In particular, the way this was phrased is assuming that you have a large set of data, imagine ImageNet, you've trained it in a supervised way, but then there is a change in the kind of images people look at, and you get new and new data, but this data is unlabeled. And this created like a particular variant of continual learning where the first task is supervised, everything afterwards becomes unsupervised or self-supervised or whatever you'd like, but something that doesn't require labels. And it's a particular continual learning problem. And interestingly enough, as soon as you start solving this particular problem, you find that the tools that you have, they're not, you know, not all of them transfer. Certain tools don't work anymore, and you need to kind of be a little bit more careful about how you phrase things. In particular, since the usual objective of maximizing performance on all the tasks so far doesn't make sense anymore, because you actually, you know, like in all scenarios, when you have the self-supervised objectives that come afterwards, the following tasks, you actually don't really care about the performance for those explicitly at all. You just care of those to fix your representation enough such that the supervised, you know, objective still works on the new data. So it's kind of an interesting thing, because the follow-up tasks, you don't really have the objective you'd like to minimize. And this gives a variant of continual learning that I think could be interesting. However, if you think of this and you try to move this to language modeling, you might actually get like a different scenario, because the question of labels is different when we deal with language, right? Especially when you do language modeling and you just do next word prediction, then you don't have an issue with labels. And then it's a very interesting question when you think about language models and trying to keep them up to date, and how do you deal with downstream tasks, and how do you make that protocol fair? So anyway, this was one example that I was thinking of. The other example that I think it's a little bit less talked about is RL and multi-agent systems. So I think a lot of time when we're thinking about continual learning and RL, we end up in a scenario where we build this kind of typical continual learning protocols, right? We string along a bunch of Atari games, or we string along or whatever. But RL on its own is a continual learning problem. It's just a very specific one. However, is one that I don't think has been studied very carefully from a continual learning perspective. And kind of the same thing happens with multi-agents. And I would say in general, you know, maybe I'm going to end up eating my words, but I say in general, the deep learning, the deep reinforcement learning community doesn't take into account the interaction between the function approximator that you kind of need to use in this kind of system, so the neural net, and the RL objective and the RL setup, right? And continual learning is exactly a disinterference. It's not about how you formulate your loss, which is usually what RL focuses on, but actually because this loss ends up to generate a non-stationary learning system, how does the neural net deal with that? And how can the neural net learn efficiently in a setup like this? And I would say, by and large, many times when people deal with this problem, it ends up being solved. I don't know if this is the right word, but mostly through brute force. So, like if you think about typical RL, you know, you have the replay buffer, and you have so this is something that's trying to make things a bit more IID for the neural net to learn efficiently. Or if you're taking something like StarCraft, you know, you end up, or like the typical multi-agent, or like a typical multi-agent system, you end up having these leagues, or when you do self-play, you need to keep track of multiple previous agents so that you don't regress on any of them, and you kind of need to sample them and play with all of them simultaneously. So all of these are continual learning problems that could potentially be solved with continual learning tools. But as far, I feel like the continual learning community and say the multi-agent community or the RL community, they're not trying to approach it this way, at least not at this scale, right? You can build continual learning problems out of RL problems or out of multi-agent problems, but not necessarily think of the RL problem itself as a continual learning problem and trying to solve. So I think this is, again, maybe an interesting application of where you think, like, why are you doing continual learning? You might be doing continual learning because you want to have a very efficient RL agent at the end, learning system, and you want to use these tools to get there. And this is, again, a very specific kind of continual learning problem. Another thing maybe connected to the first example that I gave is OOD generalization. So I've seen, I mean, the community is becoming more and more, trying more and more to address this problem. It's becoming a big conversational topic where the amount of efforts and thinking that goes in how to deal with OOD generalization, I think it's growing over time, and it will keep growing over time. But in my mind, the question of OOD generalization itself is just a side effect of the typical static learning regime. And a natural question is, what would happen in a continual learning system? And what would be OOD generalization there? And I think Hava actually mentioned this, and it was sort of a main theme in her presentation as well. But again, if you think about this, it becomes like the requirements that you want from the CL system become a lot more specific, and it becomes a little more tangible exactly what forms of continual learning you'd like to study or not. So I'm not sure how I'm saying with my time. I'm just trying to be fast. Another example.
Sorry.
Okay, 1 minute. So yeah, another example, and this is something I've been very keen on myself, is thinking about credit assignment in neural networks, right? So you'd have this issue of how HGD works. It comes with this kind of tug of war dynamics, and this is basically leads to inefficient learning. So you could think of continual learning as a mechanism that would help you to learn very efficiently from data, even if you're in a static regime, even if you're just doing ImageNet with a fixed data set. You can still think that one way of learning is by ingesting that data in a non-ID way and building on what you've learned in such a way that you can learn very efficiently without needing to go 90 times through the whole data set. Just go once or just go a few times and you've learned the data. So I think there's definitely a place of CL as being a tool for efficient learning and a tool for understanding learning dynamics and learning sort of how HGD is supposed to work and how credit assignment should be done in neural networks. And then just two more other examples. You have skill acquisitions. This seems quite related with the other things, but again, if you think about skill acquisition in robotics, then a lot of the constraints, like things that we're worrying about, like catastrophic forgetting, become somewhat meaningless, right? And the focus becomes something different. Is, okay, if I have all of these skills, how can I search to find the right one? When do I know that I need to learn a new skill or incorporate what I've learned so far as a new skill that I put in this sort of dictionary of skills that I have? And this, again, a new form of continual learning. Or you could be interested in continual learning just to understand the relationship between AI and like human learning, and it could be that could be the driving force. And I guess sort of the big questions that I've been thinking about is I'm wondering, and I'm trying to see whether this is a pragmatic way to build a taxonomy of continual learning. And I'm actually, so those are sort of the open questions that I wanted to leave the talk with. The other thing is, do we think there's going to be a single solution that will solve all these kind of things? And I'm not that sure. There's definitely a common theme in many of these things, which is this idea of requiring knowledge in order to learn efficiently new things. But I don't think that is enough to tell us that there's going to be one CL solution. And then maybe we need to have different things for different problems. And the other thing is, since the data is so crucial in deciding sort of how much we care about different aspects of continual learning. I just want to, again, push for, we need to build benchmarks that reflect the problems we care about, and ask the question of why do we always get stuck in playing with like split MNIST and split CIFAR in different ways, and can we actually learn something substantial from those, or even Atari for that matter? Can we learn something useful from that moving forward? Sorry, I'll just stop my talk here. Thank you.